All right, class, we are here today to look at an example dealing with work. And depending on whether or not you're viewing this from the Physics 1 class or my honors Physics 1, this is either example 2 or example 3 from our notes. So pretty much the statement of this problem says that we have a crate. It's being pulled across the floor by a truck. It is moving at a constant speed. Of course, this right here is always something I want to look for. When I see that, I'm thinking acceleration is equal to 0. And we're given the coefficient of sliding friction. Okay, so sliding means that it is in fact moving. And what we want to find here is we want to find work done by the truck, which is what's pulling it. We want to find work done by the friction, which is what kind of hinders its motion, and we want to find the net work done. All right, so let me go down. We're going to start off with a free body diagram of our situation here and see what we can fill out there. So first of all, we do have a crate being pulled, and again, it was on the crate by a truck. I meant to use blue for this. I'll do that for the rest of them. We do have the earth pulling down on the gravity is what causes the crate to be pulled down. We have the floor pushing up on the crate, and friction is caused by the interaction with the floor as well. So it's again on the crate by the floor. Now looking at this, oh, and I guess I should mention one other thing here. We've already mentioned it, but basically the acceleration is equal to 0. Remember, constant speed, okay, constant speed. So looking at this more from the kind of the kinematic side of things, we were told that, let's see, I'm looking it up here. It looks like it was moving 30 meters. Okay, so we'll make our displacement a positive 30 meters. And since it's at a constant speed, our initial velocity here and our final velocity here are the same value. Again, indicated here by the acceleration of 0. So basically, from this standpoint, these values here for the kinetic energy and potential energy are going to remain unchanged. Okay, we're not going to make this thing get faster. We're not going to make it get slower. It's not getting higher. It's not getting lower. So there is no real change in the amount of kinetic or potential energy that we have. So basically, the work is being done between these two snapshots, and this is ultimately the goal of what we're trying to find. So let's go ahead and summarize some things out here. We do, of course, know we want to find the work done by the applied force. That was the force to the right. We want to know the force, how the force of friction does work. That's going to be to the left, the force of friction was. And then, of course, the net work done as well. Some other things we already know. We are told that the coefficient of friction was 0.35. We were told that the mass of the crate was 350 kilograms. And again, we're not necessarily going to give the number here, but the acceleration for this problem is 0 meters per second squared. In other words, it does not change its velocity. So let's go down and come up with a strategy on how to solve this. So as we think about how do we do work here, since there's no change in energy in our problem, basically what this is going to come down to is using the work equation. Now, to use the work equation, we do need to know about forces. And at this point in time, we don't know about that. So my suggestion here is we're going to use a net force equation from our dynamics unit and figure out what these forces are equal to. So let's go over here and actually start this out and implement it. So basically, what we have is we're looking at the forces in the x direction. The acceleration in the x direction, I meant to use orange for this. Let me get down my orange pen. The acceleration in the x direction is 0. So in other words, these two forces, the applied force and the force of friction, when we add these together, they must balance out and give us a 0. So magnitude-wise, if I substitute in the magnitudes here, the force applied plus, and again, you got to remember the force of friction was a negative force, these are going to have to equal to 0. If you do the algebra here, basically what you're going to find is that the applied force does in fact equal the force of friction. And again, this is the magnitudes of these two. Now, the issue is here at this point in time, we don't have the applied force and we don't have the force of friction. So that means going out, finding another equation to do this. So the problem is we didn't have the force of friction, so we would need to actually solve for that with an equation. And it just so happens we do have an equation for the force of friction, and what we have to remember from our dynamics unit is that the force of friction does, in fact, equal mu, which is the coefficient of friction, times the normal force. Now, the issue here, once again, we kind of run into a bit of a stopping point, is that we don't have the normal force. So the normal force was a force that was in the y direction. It was an upwards force. So I think what we're going to have to do is we're going to actually have to go back to the y direction and find that force as well. So we're going to need another step to do that. So step 3 here is we're going to need to use a net force equation in the y direction to solve for the normal force. Why do we need to do that? Because we need to know the normal force to find the force of friction. Why do we need to know that? Because we had to calculate forces in the x direction to be able to find the work done. So let me go down here where I'm going to actually do that work, and we will see what we get. So one thing to remember here is that the acceleration in the y direction is in fact 0, so we know these two forces have to cancel out. We have the force of friction. No, we don't, not friction. How about the normal force? That was a y direction force. And we're going to add that to the gravity force. And again, these are vectors. And vector-wise, these things cancel out. We called up positive, so looking at their magnitudes only, that would be the positive plus the negative direction force of gravity, and that has to equal 0. And let me just zoom out just a little bit here. And basically what that means is that the normal force, if we solve this out, is going to equal the magnitude of the gravity force. Something else to remember is that the force of gravity acting on an object can be calculated by taking the mass of the object times the gravitational pull here on Earth, which of course is a familiar value of 9.8. Step 4 is going to be using the 3 previous steps. Basically, we solve for the normal force in step 3. We can substitute that into the force of friction from step 2, and then in the applied force in step 1. So let's go over here and actually take a look at what that's going to look like. Basically, from step 1, we had the force applied was equal to the force of friction. Now, the force of friction was equal to mu times the normal force. And we also know that the normal force was equal to m times g. So basically what this comes down to is that the force applied is equal to mu times m times g. And these are all values that we actually know at this point in time. So I can substitute in the mu was 0.35, mass was 350 kilograms, and gravity is 9.8 newtons per kilogram. Now when you do this math, what you're going to end up with is 1,200.5 newtons. So here we are. This should be the last step. But basically, we can use the work equation that we're familiar with. Work equals force times the distance, or force times the displacement. And basically, we're just going to substitute in the values that are for the appropriate force. So let's go over and actually try that. So in part A was finding the work done by the applied force, or I think it specifically said by the truck. So basically, this right here is going to be the applied force, which we actually calculated out. So basically, let's substitute in our numbers. This was 1,200.5 newtons, and the displacement was, let's go up and look at that again. Displacement was, where's it at here? Displacement looks like it's like a positive 30 meters. So that's going to be positive 30 meters. So 30 meters. So this is a positive, and this is a positive. When you do the math, you end up with 36,015 joules. Likewise, in part B was finding the work done by the force of friction. So force of friction is the force that we want to substitute in here. And this force of friction was opposing the applied force, and it's equal in magnitude. So basically, it's a negative 1,200.5 newtons, and that's multiplied by the positive 30 meters. And likewise, what we're going to end up with here is a negative 36,015 joules. In our last one, what we're trying to find is the net work done on this box. And in that case, we want to substitute in the net force. So basically, our net force is 0 times 30 meters. And doesn't matter how far we've actually moved it here. In this case, it's going to be 0 joules worth of work done. To summarize, the work done by the applied force, in this case it was a truck doing the work to a crate, is going to be equal to the 36,015 joules. But opposing that is the friction. So it's going to actually do the negative value worth of the same amount. So the magnitude is the same. The value is negative because it's kind of like subtracting away energy. And likewise, since the net force is 0, acting on this object, we're going to have 0 joules. Another way to look at this is that you can simply take this work minus this work, and you end up with 0 joules as well. And lastly, I guess another way to think about this in terms of energy, and I hope this will come out in later videos, because we're really not changing the overall energy of our system. Okay, we're really not adding energy to it or subtracting energy to it from it. The net work done on this system is in fact 0 joules worth of work. But that is for future examples that we're going to look at.